Well, welcome to day 8 of ATMOS 2750. Today we're kind of switching gears. We've been dealing with air pollution issues before, and now we're going to provide you with the basics of the ozone science so that we can understand the formation of the ozone hole. And I could have chosen lots of different modules to look at the intersection of science and policy, but I've chosen the ozone hole because it's an example of how science and politics can work well together to solve an environmental problem. And we'll use that as a counterpoint to understand how science and politics have not merged well together in the issue with regards to climate change. So in this particular one, we're going to introduce the ozone layer, talk about how it forms, where it forms, and what are the threats to the ozone layer that we have to worry about. Then we'll also talk about how the ozone hole was discovered. It's a fascinating story, and I want to share that with you. So what exactly is the ozone layer? Well, it's a layer of elevated ozone concentrations located in the stratosphere. Typically speaking, the maximum ozone concentrations are generally about 25 to 30 kilometers above the surface, although that varies with latitude because the height of the tropopause varies with latitude. And the concentrations in the ozone layer are high, but not extremely high compared to other variable gases in the atmosphere. So for example, in the troposphere, the maximum ozone concentration is usually typically around 0.1 parts per million. So that's 100 parts per billion. Recall that the federal standard for National Ambient Air Quality Standards is 70 parts per billion, or 0.07 parts per million. So we do get unhealthy concentrations of ozone in the troposphere. If you were to breathe stratospheric air, however, the concentrations are typically around 10 parts per million. So more than a factor of 100 higher. And so that would be extremely hazardous to breathe, because the ozone itself is a very reactive gas and it reacts with the tissues in your lungs. So this is the whole Jekyll and Hyde. Ozone in the stratosphere is good. Ozone in the troposphere is bad. In fact, the ozone in the stratosphere is absolutely crucial for life on our planet, as will be explained in the next few slides. But before we can do that, we have to have a way to quantify the amount of ozone that is in the atmosphere. And the way that we typically do that is to describe it in terms of Dobson units. So what the heck is a Dobson unit? Well, if we take a column of air that's 1 centimeter by 1 centimeter area, and extend it from the surface from 0 kilometers all the way up to space, which is essentially defined as 100 kilometers. And we integrate essentially or sum up all of the ozone molecules in that layer, regardless of where they happen to be. We know that most of them are going to be in that ozone layer between about 20 and 30 kilometers, or 20 and 35 kilometers. That's where most of the ozone is going to be. And then we count up the number of molecules in that column. And for every 2.7 times 10 to the 16th molecules, that's defined as 1 Dobson unit. And now you're going, where the heck does that number come from? Well, the number actually comes from the second bullet point here, is if you take all of that ozone in that entire column and were to bring it down to standard temperature and pressure, so down to sea level at 15 degrees C, then 100 Dobson units of ozone would take up a layer of 1 millimeter of pure ozone at standard temperature and pressure. So the way the Dobson unit was actually defined was as 1 millimeter of a gas at standard temperature and pressure, and then backtracked out to get the number of molecules per centimeter squared. So 100 Dobson units is 1 millimeter of ozone at standard temperature and pressure. And we refer to that as a total column abundance of ozone. And in the atmosphere, the average total column abundance of ozone over the entire planet is about 300 Dobson units. So that's really a layer that is 3 millimeters thick if you bring it down to standard temperature and pressure. That's about the thickness of a nickel. And that's the only thing that is protecting humans from destruction from harmful ultraviolet radiation, is a 3 millimeter thick layer of pure ozone. Think about that, 3 millimeters between you and death. So what are the properties of ozone that make it good when it's in the stratosphere? Well, on the left, we have a figure that shows wavelength on the x-axis and the absorption cross-section of ozone on the y-axis. So high values are good at absorbing a certain wavelength, and low values are not very good at absorbing a specific wavelength. And of course, the wavelengths that we have here on the x-axis vary on this particular chart from 150 to 400 nanometers. So 400 nanometers is basically violet light. And then you go to 500 nanometers, you're talking green light. And by the time you get to 700 nanometers, you're talking red. So we're looking at wavelengths that are shorter than violet light, which is why we refer to this as ultraviolet radiation. And ultraviolet radiation can further be subdivided into 3 different bands of radiation: UVA, UVB, and UVC. So UVA is the least energetic of the ultraviolet radiation, and when it's closest to the wavelength of violet light. It extends from 320 to 380 nanometers. UVB is more energetic because radiation gets more energetic as you move to lower wavelengths. So UVB ranges between 290 nanometers and 320 nanometers. And then we have UVC, which is the most energetic of the ultraviolet radiation, and it ranges between 250 and 290 nanometers. If you go below 250 nanometers, you start to get into the range of X-rays. And so what you can see here is that ozone is a very good absorber of UVC radiation, the most harmful radiation. It's a moderately good absorber of UVB radiation, and it's a weak absorber of UVA radiation. And so when you have this layer of ozone in the stratosphere, there's enough ozone there to completely absorb the UVC, to mostly absorb the UVB, and to absorb some of the UVA. And without that ozone layer, the ultraviolet radiation would essentially sterilize the surface of our planet. And before the ozone layer formed, life was only possible in the oceans because it only takes, an inch or so of liquid water in order to completely absorb the ultraviolet radiation, and you can have life that forms below that location in the water. This is one of the reasons why Mars doesn't have an ozone layer, and so the surface of Mars is bathed in harmful ultraviolet radiation, and it's one of the reasons why you don't expect to find life on the surface of Mars, and if you do look for life on Mars, it's most likely going to be subsurface. And the ozone layer itself was discovered in 1913 by 2 French physicists. So here we have the total column abundance in the Earth's atmosphere as a function of latitude. And you can see that the average total column abundance is about 300 Dobson units if you look at all the different latitudes. What you will notice is that there's some variation. And in the tropics, there's actually less ozone in terms of the total column abundance than in the mid-latitudes and the higher latitudes. So what that means is that if you happen to be in the tropics, you're actually more likely to get a sunburn for 2 reasons. One, because the sun is more directly overhead, so there's less scattering of the radiation. And also, there just happens to be less ozone in the tropics. And one of the reasons for that, which we'll get to shortly, is that ozone formation and destruction are occurring simultaneously in the stratosphere. And it's the local rate of production compared to the local rate of destruction that determines the amount of ozone in the stratosphere. And in the tropics, there's a slightly faster rate of destruction than there is in middle latitudes, so you consequently have a lower equilibrium concentration in the tropics. That has one other implication in that the rate at which you have mutations, cellular mutations due to interactions with ultraviolet radiation is actually higher in the tropics. And as a result, the rate of evolution of species is actually latitudinally dependent because of the latitudinal variation of ozone. So here's another plot which essentially shows the same thing, but also shows the longitudinal variation of ozone. And you can see once again that most of the tropics have total column abundances of ozones that are less than 260 Dobson units, and above about 35 degrees north and south of the equator, you get to your average of 300 Dobson units. And as you move poleward into the middle latitudes and the upper middle latitudes, you end up with higher concentrations all the way up to even over in Asia, all the way up to 380 Dobson units. You also notice that there is some variation between land and ocean, although I'm not 100% sure of the cause of those variations. So let's talk about ozone formation in the stratosphere. So this is naturally occurring, and we have diatomic oxygen, which makes up 21% of the atmosphere. When it interacts with certain wavelengths of ultraviolet radiation, it will photolize and essentially split apart. That strong double covalent bond will break and give you monatomic oxygen. And then that monatomic oxygen is going to collide with other gases in the atmosphere. The most common gas that it's going to collide with is nitrogen, because that makes up 78% of the atmosphere. The second most common gas that it'll collide with is diatomic oxygen, because it makes up 21% of the atmosphere. And it just so happens that if a monatomic oxygen collides with a diatomic oxygen and collides with a third molecule, which is going to most likely be nitrogen, but it doesn't necessarily have to be nitrogen, that collision, that three-body collision, will absorb enough energy from the species that it will allow the monatomic and the diatomic oxygen to form an ozone molecule, O3. And the net chemical reaction for this naturally occurring process is 3 diatomic oxygens go to 2 ozone molecules. But it requires the presence of ultraviolet radiation. So this is a daytime phenomenon for the production of ozone in the stratosphere. So naturally occurring destruction of ozone also occurs, and there are 2 mechanisms where that happens. One is you can have photolysis of ozone. Photolysis, remember, is the destruction of the species due to interaction with ultraviolet radiation. That can break it apart into monatomic oxygen and diatomic oxygen. So that is a process that occurs during the day. The second reaction here, it occurs when monatomic oxygen reacts with ozone to create 2 diatomic oxygens. That occurs 24 hours a day, day or night, just whenever a monatomic oxygen happens to collide with an ozone molecule. There's a probability that it will basically react. And so the net chemical reaction of this ozone destruction mechanisms is 2 ozones go to 3 diatomic oxygens. And if the destruction is slower if ozone destruction is slower than the formation of oxygen, it's more likely to hit an O2 molecule than an O3 molecule. And these 4 chemical reactions were postulated to occur by Dr. Chapman in the 1930s. And he said if these 4 reactions are occurring in the Earth's atmosphere, then we will indeed have an explanation for the Earth's ozone layer, because that's what these equations will lead to the formation of ozone during the day, and then the reaction rates are slow enough that the ozone persists through the night as well. So next I'd like to talk about Crutzen, Molina, and Rowland, who were the first to identify threats to the ozone layer. Paul Crutzen completed a modeling study in 1970, and he showed that nitrogen oxide and nitrogen dioxide, collectively known as NOx, could catalytically destroy ozone in the stratosphere. And as a result, the US pulled all money from the development of the supersonic transport aircraft that it was working on. So the Europe was working on Concorde, which was a supersonic transport airplane, and they continued to build it even though the United States decided that the risk to the ozone layer was very high. And the reason being that the supersonic transports fly very high. They actually fly in the stratosphere. The engines burn very hot, which actually converts a lot of the nitrogen in the atmosphere that moves through the engine to nitrogen oxides. So they would be putting a lot of nitrogen oxides into the stratosphere. And then in a separate study, about 4 years later, Molina and Rowland were conducting laboratory experiments to see what types of molecules might react catalytically with ozone. And they discovered that chlorofluorocarbons could catalytically destroy ozone in the stratosphere. They knew that the chlorofluorocarbon concentrations in the atmosphere were rising and that they would eventually make it into the stratosphere. And they actually predicted the formation of an ozone hole over Antarctica in 1974. So that was about 12 years before it was actually discovered. And eventually, Crutzen, Molina, and Rowland were awarded a joint Nobel Prize in Chemistry in 1995 for their work at basically looking at the potential harms or pathways for destruction of ozone in the stratosphere. So why are they concerned? What are these catalytic destruction cycles that these Nobel-winning scientists were so concerned about? Well, if you have a catalyst in this series of chemical reactions, the catalyst is the species X, and we'll keep a mystery about what X is right now, but a catalyst is a species that initiates a chemical reaction and then is consumed, but then is recreated in a subsequent chemical reaction so that it's available to start the chemical reaction sequence all over again. So in this case, we have ozone that reacts with the catalyst, and you now have an oxygenated catalyst and O2. So we've destroyed the ozone. This oxygenated catalyst then reacts with ozone again to give you back the original catalyst plus 2 diatomic oxygens. And the net result of this is that 2 ozones are transformed into 3 diatomic oxygens, and the catalyst remains to do this cycle again. And so it's this catalyst will continue to destroy ozone until it's rendered inert by going through a different set of chemical reactions. And as a result, one catalyst molecule can destroy thousands of ozone molecules before it's rendered inert. And the known catalysts for ozone destruction include the nitrogen oxides that Paul Crutzen identified in 1970, NO and NO2. Then there's chlorine, which was identified in the laboratory experiments from Rowland and Molina. The chlorine is a component of the chlorofluorocarbons that they were concerned about. And then subsequently, research has identified bromine and fluorine as other species that can act as a catalyst in the above chemical reactions. So let's talk a little bit about the discovery of the ozone hole. So at Halley Bay in Antarctica is the location of the British Antarctic Survey. And they were conducting daily measurements of the ozone total column abundance in the atmosphere that started in 1957 and continues to this day. And I've shown a subset of their data over on the right. Recall that the average concentration total column abundance is about 300 Dobson units. And so from 1957 to the early 1970s, the total column abundances at Halley Bay were roughly bouncing around that 300 Dobson units. And then in the mid to late 1970s, they started noticing that the ozone total column abundances in the Antarctic spring, so all of these measurements are actually taken in the spring months, the spring for the southern hemisphere, and they started noticing that the total column abundances were dramatically decreasing. And in fact, by 1983 or 1984, the total column abundances had dropped by 1/3, from all the way from 300 Dobson units down to 200 Dobson units. And at that time period, they decided that they had to publish a paper in order to get the word out on what was going on down in Antarctica. And so they tried to publish their paper, which at this point was built upon 26 or 27 years worth of data, and the paper was rejected. You want to know why the paper was rejected? Because they didn't believe it. They said, well, this is really interesting. You should go back and check your measurements because we think something is weird. We think something is weird because NASA has a satellite that is observing the total ozone concentrations, total column abundances of ozone, and NASA hasn't seen this reduction. So there must be something wrong with your measurements. So the scientists from the British Antarctic Survey went back and they went through all of their calibrations and they went through all their procedures and nothing had changed. And they said, nope, our data is good. NASA's data must be wrong. Have NASA go back and check their data to see if there's in fact a decrease in the ozone total column abundances. And so NASA went back and checked their data and they didn't see the decrease. But when they looked at their code had one line in it that said if the total column abundance of ozone is less than like 270 Dobson units, then it must be a bad measurement and we'll just throw it out. Big problem. When they took that one line of code out of their computer software, lo and behold, what did they have? They had an ozone hole. And so looking at the ozone total mapping spectrometer satellite data from 1980, this is what they saw. This was a pretty big, substantial decrease in the ozone total column abundance over the entire Antarctic continent, with total column abundances down below what was being measured at Halley Bay, actually down below 200 Dobson units. Oh my gosh, this is a big deal. And this wasn't apparent in the NASA data until they corrected their algorithm. So now let's step through subsequent years to see the evolution of the ozone hole over time. So this was 1980, 81, and so forth. Notice by 1983, when the British Antarctic Survey was trying to publish their data, the ozone hole was quite large, covering essentially the entire continent of Antarctica, with much of the Antarctic continent less than 200 Dobson units, which is basically the transition from blue to purple in this particular color scheme. 1984, it got much larger. 85, large and deep. So by 1990, it's now larger than the Antarctic continent, and there are places where the Dobson units are now less than 150. By 1991, we had our first incidence of Dobson units down to 100. So the ozone was 2/3 gone at this location in the center of Antarctica in 1991. And in this case, the Antarctic ozone hole extended all the way to the tip of southern South America. This actually led to cataracts in the eyes of rabbits. And there was a whole generation of rabbits in southern Patagonia that were blind. And you could just go up and grab them because they couldn't see you coming. 92. And then I skipped a little bit up to 96. 1997, large areas of Antarctica are now below 100 Dobson units. 2003 was a particularly bad year for the ozone hole in terms of size and the concentrations inside. So there is some interannual variability, and that interannual variability has to do with the strength of the polar vortex. Two 2009 was once again a bad year. NASA occasionally changes the color schemes on their animations.